So first of all, thanks to the organizers for inviting me. This is my 6th day in India, and if you're asking yourself what happened to my head, it's not I'm trying to actually put any Indian sign. I just I didn't pay enough respect to the Maharaja, and so I didn't take down my head and I hit the frame of a door. So, but everything is under control now. So, what I will talk about today is joint work with Bart van Rossum from the Econometric Institute Erasmus University in Rotterdam. So, Bart was a visiting student in New York. Around essentially 1 year ago. We worked together with my, at the time, postdoc Ray Chen, that is now at the Chinese University of Hong Kong in Shenzhen as an assistant professor. So we started looking at essentially fairness type of problems, and something that I've been working on a lot with the Shriram, and eventually we kind of moved to a particular type of idea in integer programming that I would like to talk to you about today. So the motivation is indeed, as I was saying, is fairness, and the idea behind the scene is this. So if you're, for example, you take your maybe favorite optimization problem, like I don't think that the vehicle routing is my favorite optimization problem, but let's say it is. And this is actually the problem in which we have one depot, and we have 1, 2, 3, 4, and actually 5 vehicles that are visiting clients. So this is the optimal solution of the problem, in which there are significant differences between the lengths of the routes. Okay, so maybe one driver is going to drive a lot, and another driver is going to drive much less. So the total distance traveled here is 6,178 in some unit. And the range between the longest route and the shortest one is actually, the difference is 2,176. However, if you allow yourself only to pay a little bit deterioration in the efficiency objective function, so minimizing the total distance traveled, you go from 6,178 to 6,181, so only 3 difference, but you actually gain a lot in terms of the distance, the difference between the maximum length and the minimum length, okay? So going from 2,170 to 1,601, okay? So the motivation is indeed that the range is a commonly used objective function for fairness oriented type of problems. You can think about this as bijective optimization problem, in which you are trying to look at the efficiency component and the fairness component. Recently, Moshe Vardi visited Cornell Tech, and he gave a very inspiring talk about another third pillar that optimizers should look into, take into account. So one is the efficiency that we have been, paying all our attention for decades. Then fairness is raising up a lot. And Moshe was talking about resilience, right? I mean, you want solutions which are also resilient, because as we have seen during the pandemic, being very, very optimized led us without toilet paper in New York City, and maybe that was not, in the US, which is, can be annoying. So now these 3 pillars, I will not talk about resilience, even if I think it was a great inspirational talk. Here we are talking about at least taking into account the fairness perspective, and there are people in the audience have been working a lot on this. Shriram was one, Swati is actually the expert here, so, and she already attended one of my talks and gave me a beautiful we still have to talk about that point, so exactly, we have to look into that. So this talk is about primarily looking at the perspective from an integer programming formulation, and I try to see to talk about the idea of improving the classical formulations that you can think of is when you go from extending a formulation that is designed for efficiency to actually take into account also the fairness. And I will try to convince you that this generally leads to a weak formulation, so formulation in which it's much harder to optimize versus the one that has been designed already with having in mind the perspective of the efficiency. But we have some, what I will propose to you today is that we have some ways of dealing with this by, for example, branching. So what we will focus is range minimization with, in particular, formulations that are generally taking into account exponentially many variables, columns. You can think about routing problems, which is our main motivation, but also crew scheduling and many other problems like this. I will also finish, if I have time, the talk with giving you some let's say, counter-intuitive also situations in which, at the very end, in which the normal formulation to deal with a problem, particular problem, which is actually the generalized assignment, is not an exponential size formulation, but as soon as you introduce constraints of the form of the range minimization, that you want actually to think about going to that formulation because that would be better to use. So kind of counterintuitive. So, yes, so again, from a motivation perspective, also weak LP relaxation, you can think about the vehicle routing that I presented you before in this way. So we have 5 drivers here, or 5 routes. So each one of these little bars represent the particular route which the driver or the vehicle is driving. So now, of course, in an optimal solution, there will be only one route per vehicle, but in a fractional solution, which is the LP relaxation, I can drive multiple routes a little bit, right? And so the height of the bar represents how much I'm driving on that particular route in the fractional solution, and this in this direction you think the length of the route. Okay, so now if you since you are driving in this particular case 4 different routes, you take an average, weighted average of this, and this D1 bar is the distance traveled by driver number 1 on average. And this is actually, you can see immediately that the LP relaxation is going to cheat on you as much as possible, right? I mean, it's like you're going to tell you that each driver is driving exactly the same, which eventually leads to an objective function which is equal to 0, which is, of course, terrible because it can be thought arbitrarily far away from the optimal solution. So now, the outline of the talk is we'll try to look at into branching rules that are taking into account both fixing variables and bounding those variables, especially the objective function. We talk about some theoretical properties of this branching, and then we evaluate the performance on a couple of applications, extending a little bit the framework beyond range minimization to a more general type of objective function. So now, let me describe the problem formally. So let's assume that this is my set of constraints. I want binary variables and a set of capital N binary variables, a set of linear inequality, AX less or equal than B. This is describing my problem. And let's say the feasible solutions of my problem, which are let's assume that at the moment AX less or equal than B doesn't take into account the part which is associated with the fairness perspective. Okay, so now each one of the variables has associated a certain payoff, and I can define the P max as the maximum of those payoff and P min as the minimum of the payoff of the variables which are in the solution. So Xi is strictly greater than 0. So which means that this P max and P min are also associated with columns or variables which are not taken at 1, but just slightly in the fractional solution are just slightly used. So maximum minimum payoff, then assuming that I can formulate the range minimization, so taking into account how to write Pmax and Pmin, then the objective function will just be the difference between Pmax and Pmin, the payoff, you can think about the cost, the payoff, or whatever else, and over the set of linear constraints with integer variables. Since, I will not use it explicitly anywhere, but let's assume that this AX less or equal than B is also taking into account a sort of deterioration factor with respect to the most efficient solution. So let's assume that in the VRP I'm solving the problem to optimality and I'm saying, well, I want to be fair, but I cannot pay more than 10% or 20% of what of the optimal, my optimal cost, efficiency cost, and I can include this as a constraint in my problem. And of course I can play with that constraint in any form.
So this difference Pmax minus Pmin, this particular way of defining that's very specific. There could be other ways, right? Because
of course.
Just saying that if it's 0-1 solutions and you're getting right.
Yes, we are actually targeting here. You will see some extensions towards the end, but we're targeting really situations in which, and this is the way I was talking about starting from this idea of fairness and fairness over time that I was working with. I'm still working with Shriram. The point is here the twist that we're taking is the fairness is associated with different players that are composing a solution, right? The players are each one as building a solution, and then you don't want the players to actually be too different. But it's of course that's a very restricted type of problems that you're thinking of.
So my point is,
there's also the objective function. Yeah. Yes, absolutely.
Converging to the integer objective.
Yes. So now, the assumptions here is that we have a large number of columns, and so the choice, the method of choice for solving this problem is going to be branch and price. So you are generating columns at every node of the LP relaxation. And we're also assuming, which is not too restrictive, that we are able to actually modifying our pricing algorithm or branching scheme in order to take this situation into account. So the P of P can be conveniently incorporated into the pricing. We need some constraints involving this, and then I will be, let's say, specific in a second. So let's go back to what we propose. And again, Pmin and Pmax are defined, just to point it out again. So it's not xi to be equal to 1. Is xi any value? So in the previous picture, so if I take a particular route at a very small fraction, I'm still thinking about Pmax or the distance or the payoff of that column to be considered fully. And then I define something which is called range respecting if in an LP relaxation, x bar, eta and gamma bar, where eta and gamma will be the variables that I'm using in order to model the objective function max and min. We say that this vector is range respecting with respect to the payoff if eta bar is actually greater or equal than Pmax of x bar and gamma bar is less or equal than Pmin. So I'm taking two values that are representing the extreme of my objective function, and I'm pushing them higher than the maximum and lower to the minimum in such a way that representing correctly what I'm doing. So otherwise, this solution is range violating, and what I will try to convince you is that, it's not very difficult to convince you because this one is clearly telling you that this is actually range violating, right, immediately. It's a terrible LP relaxation. So there are a bunch of range violating solutions, and our idea is first, let's try to deal with those range violating solutions. This one?
Oh, and so the range is eta bar and gamma.
Yes. So, our proposal is relatively simple. I will go for a picture in a second, but let's assume that it's range violating. So range violating means that eta bar is strictly smaller than the Pmax, okay? So now what do? I just take a capital U, which is between eta bar and Pmax, and I construct two children by branching, saying, well, now eta, that is my variable representing the maximum, is going to be either less or equal than u or greater or equal than u. So the less or equal than u situation is actually kind of a stronger constraint because enforces all the variables, so all the routes in the vehicle routing situation that have a strictly bigger value than this u to actually fix it to 0. I can do it with only one constraint that says every one of the columns that has a larger value in the payoff, the sum of them has to be equal to 0, so those variables are non-negative, so all of them have to be equal to 0. So this node is actually, this branching, not generally, but often leads to actually fixing the node to be infeasible. So I can fathom the node directly. Otherwise, it's easy to see if eta is greater or equal than u, automatically I have to push the objective function higher. So I'm going in the direction of improving the objective function. So that's why before I was saying on the one side I have a variable fixing, so I fix a set of variables. On the other side, I actually improve, I push the bound up, okay? So, of course, if I can do the same thing for gamma, just reversing the thing is totally symmetric and there is no problem. And let's pictorially looking into what happens. Let's assume that my eta bar is here. And I have actually P4 and P5, which are actually non-zero columns in which whose payoff is actually strictly bigger than eta bar. So now I'm branching, I'm picking a u, which is actually in between of this value and the max, close in this particular case. And the good news is that I can fix both the variable associated to be, let's say, x4 and x5 equal to 0. So, and I kill everything that is in this direction, okay, with just one linear inequality. And on the other end, automatically, if I'm saying that eta has to be greater or equal than u, automatically my next eta bar is going to be at least u, right? I mean, it cannot be smaller than that. So with this simple branching rule, I'm advancing in both directions. And note that, of course, this is a proper branching rule. So when you see it for the first time here, looks like you're not cutting off this u situation, it's like in between, but technically speaking, that's exactly what you're doing because somehow the situation is that you are cutting off the previous solution in both cases. So no problem. You are, on the one side, you're fixing variables, on the other side, you're pushing the objective function to go in a certain direction. So now, which are the properties? Well, let's go back and put this, take this off of the carpet, it was under the carpet. So these are the set of constraints. If I have a general formulation in which I have this ax less or equal than b, the x variables, the objective function would be the efficiency, I don't need anything else. But if I want to transform that particular formulation in something that takes into account the range minimization, what I will do is that I will need likely a set of constraints that are taken into account the eta on the one side, the gamma on the other side, and are modeling these two variables and putting them in such a way that it's easy to write them in the objective function in that form. I'm not saying that this is the only way of writing formulations for those problems, but somehow it's a very natural formulation that everybody comes up when you want to move from the classical efficiency perspective versus towards the fairness point of view. So this is a valid formulation for range minimization problems, if of course it's feasible for this set and means that the x is respecting these constraints and the integrality requirement, and of course z is z, which is the formulation itself in which they have the x variables plus the eta and the gamma, is range respecting. So I'm respecting the constraints. Here, of course, is the full formulation, so integrality requirement included. So it's valid, and the thing is that I'm somehow saying, well, let's look at this W. Is valid when it defines a valid formulation. So let's look at W. Then the LP relaxation of this problem is defined when I just drop the integrality requirement. And so I relax 1e, and if in addition, for each range respecting, let's say, z, for which x is fractional and ax less or equal b is respected, it holds that z belongs to this LP relaxation. Then we say that this formulation is a weak valid formulation. And why is actually we call it weak? Because this formulation admits all fractional range respecting solutions. So here I'm not even talking about the range violating solutions. So I'm talking about the one that are range respecting. And how do you actually convince yourself that it's true? Essentially, think about it, is in those formulations in which you have added a set of constraints to take into account gamma and eta, essentially any valid formulation is weaker because if the constraints that you have added would be automatically cut off fractional solutions, then you can include directly in AX less or equal than B, and somehow you don't have a problem anymore. So this is automatically done. This is not done automatically in most of the cases, and so every single range respecting fractional solutions is going to be actually this valid for the formulation. So those formulations are not, let's say, naturally cutting off fractional solutions, which are range respecting. But actually there is even worse. The problem is that it's easy to convince each other that, let's say, if I take two solutions which are feasible, and I take any convex combination, I end up with range violating fractional solutions. So there are a huge number of range violating fractional solutions that are part of the formulation. And our proposal on range branching is precisely taking into account this part. So I cannot do anything at the moment. I'm not thinking about the range respecting fractional solution. I'm actually saying that what is mostly annoying are the range violating fractional solutions, and I want to target them by branching. So, and why it should be effective? Intuitively, the situation is that if I call range branching free, and a node in the branch, in my branch and price scheme, in which I don't have any more range violating solutions. So essentially I've branched enough on my proposal in such a way that the solution is range respecting. I can claim that this solution is actually better than any feasible solution of any LP relaxation. And this is exactly what this small proposition says. Essentially says this range branching node solution, which is going to be somewhere in the tree, is actually dominating any fractional solution that is at the root node of any LP relaxation possible, because essentially this is feasible for any one of those formulations, this range branching free, which means that as soon as you have branched enough, you have certainly improved the bound with respect to any other formulation that you can think of, taking into account those particular constraints. So somehow the intuition that comes out of this discussion is, well, when you just try to take into account the fairness by augmenting classical formulations for optimization problems, you end up in, let's say, in weak formulations. And the first order of business will be to take at least into account for range minimization, the range violating fractional solutions. And once you're there, essentially you can really start your process altogether. Let me give you a pictorial intuition of why this is true. Again, this is our original motivation. As soon as I add one single iteration of range branching, immediately what I have is I fixed a lot of stuff on the one side, and now I have the D2, for example, bar, which is the one of the second driver, is actually here, the one is here, 3 and 4 are still there, 5. So now I already have, with one branching only, a significant difference in the max versus the minimum, and so I moved the objective function significantly up, okay? So now, there are some practical considerations which I don't think are super important. So of course, one question is the value of u, right? I mean, how do you pick u? You want to be very aggressive, going very, very far. You want to stay closer. So there are a bunch of things that you can try. And there are improvements that can be performed here. For example, finding good heuristic solutions. So heuristic rules for building primal solutions, and so on and so forth, but that's not so important. So I would like instead to give you a flavor of what is actually the computational part of this, because, I mean, it sounds like a decent idea, but it's not obvious that it actually has a significant impact in practice, right? So now, the problem that I will play mostly is this fair capacitated vehicle routing, in with that now I want to define them more properly. So C, capital C is my set of customers, H1 has a demand DI. K, I have capital K identical vehicles, so with capacity Q. I have a symmetric arc distances Cij for every node, every pair of nodes Ij, and my efficiency component is included into B, into this constraint over the maximum route cost. I mean, I can do it in multiple ways. In this particular case, we're saying that the routes cannot be longer than a certain amount. So now what I want is that among all the possible routes, capital R, I want that are starting and ending at the depot, that are respecting vehicle capacity, are not exceeding the maximum allowed total cost here. A feasible solution consists in a subset R such that every customer is covered, of course. And the optimal solution is the one that minimizes the range between the longest route and the shortest one. So I have two formulations to show you. One is the vehicle index formulation, which is somehow a classical extension of a vehicle index formulation for vehicle routing, which we know is weak. Not in my, I mean, it's not in the way I was using weak, but is generally weak for, even for capacitated vehicle routing. Because here we are taking into account so I have not only a variable per route, which is already a huge amount of variables because we have exponentially many possible routes, but I also have k copies of that variable. And this is the most classical thing that you will come up with, because this is easy now to model the constraints over eta and gamma, right? I mean, it's like, it just simply says if for every vehicle k, if I cover the route R with vehicle k, the variable is equal to 1, then PR is going to be the payoff of the route R, and eta has to be at least as big as this payoff. So this is going to be becoming the largest one, the largest of those, minimum largest, and this one is greater or equal, so the maximum gamma that is actually satisfying the same thing. So this is very easy. It's a classical extension of this formulation. We know intuitively that is a bad formulation for the vehicle routing. It's not going to become any better for our fair vehicle routing. So there are better formulations. And one of them, which has been recently proposed, is not proposed by us, is actually this ingenious type of idea. It's called the last customer formulation. So this one has significantly less variables. I don't need the k copies of each one of the routes. And I just have a variable xr per route that, so the constraints are for covering, this is the length of the route, I need to select exactly k routes, and here, so the idea is I have this parameter BIR, is a parameter saying if customer I is the last customer of route R. In this way, you are able to select, you have a constraint per customer. So this constraint is actually enough for telling you that for measuring eta. So this one says, well, if I look at all the routes, all the potential routes in which I is the last customer. Of course, I is covered only once because of this constraint. So there are multiple ones here, but only one of those will have the XR equal to 1. And then this is actually telling you that you have to take the largest payoff in that case. Okay? And the same thing happens for the second constraint, except that for the gamma, except that here you need a big M component in order to take into account this greater or equal version of the problem. So the big M component says, well, if I don't select any R in which I is the last one, this one will be 0, and then the big M kicks in and makes the constraint satisfied automatically. But of course, it's not a big deal because gamma has to be less or equal to this value, and so that goes in the right direction in the objective function. So this is actually kind of a nice formulation. But what is interesting to show you is, what is our scheme? Our scheme is, we started by simply taking the formulation and solving the two formulations without range branching, okay? So we have all the bells and whistles that you need for branch and price. We have the pricing and we can branch on the variables, or actually there are, for the vehicle formulation, you branch on the assignment of customers to vehicles. For the customer formulation, you branch on the last customer in order to make sure that you are doing things correctly. So there is a literature comparing these two formulations without the fairness requirement, okay? So now, what I will try to convince you is that the fairness requirement, let's say, no, without the branching, not the fairness requirement is included, but without the branching that rule that I'm proposing now. And again, coming back to my favorite example, we start here at the root node. After one branching, we are here, but after few branchings, we are really restricting the solution space because we can fix variables a lot. I mean, of course, this fixing of the variables is the one associated with gamma, right? I mean, you're fixing on the upper side when you're branching on eta, you're fixing on the lower side when you're branching on gamma. So now, these are the component of the results. So first of all, observation, fairness creates significant troubles. I don't want to say it. Let me rewind. So for optimizers, including fairness is actually slightly problematic, in the sense actually highly problematic. So we know that we can solve, not routinely, because the vehicle routing is still significantly more difficult than the traveling salesman, but we can solve well enough vehicle routing problems with 100 easy, let's say, relatively easily, unless these are very strange formulations. There are very strange problems with 100 of clients. Here we can go to 25. Okay, so this is a significant reduction. So vehicle routing, you can go even higher, maybe 200 and so on and so forth, but you really need a very specialized methods for doing this. 100 is now well understood, let's say. Here it's well understood, relatively well understood to go to 25, so which is a significant difference. So now, which formulation should I use? It's interesting to look at. This is the classical formulation versus the vehicle formulation classical or customer formulation classical, okay? So the first one or the second one I gave you. Let's forget about the range branching that I'm proposing for a second. And you say that for 15, the formulation here is the vehicle formulation solves all the problems, 20 over 20. Instead, the last customer only solves 17 of them. And then for 20 is 9 over 1, and for 25, none of them is solved to optimality in 1 hour of computing time. And the gap is, is bad in both ways. But for example, this one, 33% versus 67, okay? So per se, the last customer formulation is not a killer. So it doesn't work particularly well. However, if I do range branching, and the algorithm that I'm applying is the following. So whenever possible, it's a simple rule. Whenever possible, I do range branching. And when I'm done, so I'm in the notation that I used before, whenever I am in a range branching free node in which I already branched enough on the range violating constraint, range violating solutions, then I resort back to the original classical branch. So interestingly enough, so for 15, there is an improvement for the classical formulation. So the vehicle formulation, I can still solve all the problems in a slightly smaller amount of time and with a slightly smaller number of nodes. In the last customer, I go from 17 problems solved in 900 seconds to 20 problems solved. So all of them are solved actually in a much shorter computing time. And here I started to look at, this is actually 2 orders of magnitude faster than doing the vehicle even with range minimization. 20, the situation becomes, I go from 9 to 16 in half of the time, in 1/3 of the time. I can go from 1 to 19 in actually only 290 seconds, which is a very significant improvement. And the only one that I'm not solving is actually probably solved, but I could not prove optimality. So a smaller number of nodes and everything. And even 25, this actually the last customer formulation empowered by range branching is actually quite effective, solves 70% of the problems to optimality. Final gap is only 5.8% in slightly more than half an hour. And the last column here is the interesting is the range improvement with respect to the most efficient solution. So if I allow myself, I think that we are using like 10% or 15% here of deterioration of the efficiency. Still, I can improve of almost everywhere 50% when I solve the problem to optimality in terms of the range that I obtain, which is actually a nice practical result. Here you can see a pictorial representation. It's a problem with 25 vehicle formulation and customer formulation. So this is the one that is closer is the one. So this is, let's say, this is actually gray and this is when it was black. You don't see it super well here. But the situation is that this closes the gap faster, so dual and primal. And in particular, when, even if this instance is not solved to optimality, you can see that the way in the customer formulation, the way of closing the gap is actually quite nice. And do you see this big jump, right? Somehow, the first part, you are able to recover a lot of the gap, close a lot of the gap through range branching. And after that, essentially, you start doing what you're supposed to do most of the time, but range branching is the one that is pushing the objective function quickly there. So, 2 more things. The first one is this extension. So you can think about range minimization as a special case of the ordered-based minimization. So instead of actually just taking into account the 2 extremes, so the maximum and the minimum of the payoff, you want to take into account all the order of all the payoffs. And somehow this is very well known in data science as the Gini deviation. So in the Gini deviation, what you want is that you take into account every pair of let's say, objective function components, and this is actually the Gini deviation of the objective function. You take into account for every k the difference between the payoff of I and payoff of j, the absolute value of it, and that this can be written in this way. And this order-based minimization will be exactly the same as the one that we had before, with this different objective function, which is given by the W defined in this way, where, and for our vehicle routing problem, this is automatic, you are taking exactly k pieces of the solution. For our case, is kind of was an easy extension because the K pieces are exactly the K vehicles that we are using, but it can be a general situation. So order branching is very similar to the range branching that I defined before. So it's actually just you have to take into account every piece. And the good news is that now you are able to do variable fixing not only in one side of the branching, but in actually many of the possible, in both sides of the branching. And again, these are some results for the capacitated vehicle routing with this Gini deviation. Again, 15, 20, and 25 clients. I can, the classical formulation solves 17 problems in 1,000 seconds. The one with order branching goes to actually solving all the problems in 2.9 seconds. So the improvement is significant. 60% of the problems, even with 25 clients, are solved to optimality in a short amount of time. In a short amount, I mean, it's like in 2,000 seconds with final 18% gap. So there's still some work to be done potentially there, but you can see that the idea works in practice over there as well. So conclusions are, well, I think this is interesting. What I like about this paper is that, or this work is that we started from the fairness perspective, which I think is very, very important topic. And at the same time, we came up with something which is a very methodological from the perspective of integer programming, right? I mean, how to deal with formulations of this type with specialized branching rule, which is integer programming. At some point, it was not in the map, so we wanted just to solve this problem. We came up with this, and we decided, well, actually, it seems to be general enough that to be communicated by itself. And there is actually plenty of work potentially to do. I think we have ideas on doing the max-min or min-max. There are several variants that you can think of. And we need definitely to better computational results to have good primal heuristics. You can do a lot probably on the pricing problem to take this into account even better, and so on. So I would like to finish by actually reporting these results, which are, in my opinion, kind of counterintuitive, as I was saying before. This is actually the classical, let's say, range minimization for the generalized assignment problem, and which is a classical problem in the literature. And the interesting thing is that the column generation formulation for the generalized assignment, that's not the winning formulation. I mean, you don't want to do general column generation for this. There is a nice compact formulation that somehow solves the problem relatively well. When you add the fairness perspective, it starts to struggle a lot. These are agents with the profit. This is it's not important to actually to see how this are defined according to the literature. But here there's the three instances. For 5 agents, we can solve each problem. For 10 already, you cannot solve all the problems. And for 20 agents, the situation gets very much in trouble. And again, if I do branch and price, even for the fair version, it's not doing any better, right? I mean, this is worse than this formulation, this is worse than this formulation, this is worse than this formulation. So the trivial extension without doing column generation is not good. But if I go to the formulation, the branch and price formulation, and I add now the range branching, which is becoming natural for the column generation formulation, I actually end up to be able to solve all these problems relatively easily to optimality, which is a big boost with respect to any other thing that we have seen in this context. I don't have to be honest with you, a very good explanation of that. So to me, it's still relatively unclear. maybe one question is, can I do range branching in the original space of variables or in some form? And I don't know. But that's why at the beginning I was saying that this is kind of an interesting observation, somehow even counterintuitive a little bit, that you switching to a more standard formulation like the column generation one, that in theory will not be the formulation of choice for that particular case, if empowered by the branching on the range branching sounds like a good idea, and maybe something to try and to see if this is actually generalizable in some form. And that's it. Thank you very much.